Hello, welcome to Basics of Noise and its Measurement. Last week we were discussing the concept of Fourier transform. We started with Fourier series expansion of well-defined functions, then we moved to Fourier integrals, and then we closed the week by discussing and introducing Fourier transforms, which are representations of our time series function in frequency domain. What we will do today, at least for the first part of this week, is continue that discussion. But one significant difference will be that in the last week when we were discussing Fourier transforms, these were for continuous functions. But in reality, not necessarily in real, but in reality or where if we think about practical considerations, most of the data which we acquire from our data acquisition systems, it is not in form of a continuous function. Rather, what we have is a set of points which are discrete in nature. So we have discrete sets of points as function of time. So we have a point at t is equal to 0, we have another point at t is equal to t1, and there's nothing in between, then another point at t is equal to t2, and so on and so forth. So this is a discrete set of data, and if we have this discrete set of data in as a function of time, then how do we map this onto frequency domain? So that is going to be the focus of our discussions today, pretty much, and what we will use in that context is something known as DFT, or discrete Fourier transform. Okay, so this is essentially we have the same theory which we used for Fourier transforms, which we discussed last week, but we are mapping that information into discrete space, and these transforms are known as DFT, or discrete Fourier transform. So suppose I have a bunch of points. So we will discuss discrete Fourier transforms. And we will not prove whatever relations I am going to talk about, but we will directly state the results and then do a couple of examples to understand this whole concept. So suppose I have a data acquisition system, and it's acquiring some data, and I'm going to plot this data. On the time axis we have time in seconds, and on the y axis I plot values of this data, and I call it xn. Okay, so I get one point which may be in the beginning. So I am going to plot all these points in red. So this is in the beginning at t is equal to 0, then at t is equal to 1 second, t is equal to 2 seconds, t is equal to 3 seconds, 4 seconds, 5 seconds. Okay. So my aim is, so this is xn, and this changes with time. And xn is discrete. It is discrete. So it's not, so there is no continuous function between x0 and x1 and x2. So these are discrete points. Then the question is, if I have this type of a discrete function, then what are its Fourier components in frequency domain? Okay, what are its Fourier components? This is the question. So, this is one. And second thing we have to note, so xn is a discrete function, and also xn can be complex. If it is a complex number, if it was a real number, then all I have to do is plot xn on y axis, and on the time axis I plot t, and I make this plot. If it was a complex number, for complex numbers, how will I plot it? I will actually have two graphs. One graph will be for the magnitude of each of these points, and the other will tell us its phase. So, in that case, time, and then this will be modulus of xn, and then I will have a bunch of points. So, these are the modulus or the magnitude of this function. So, this is magnitude plot, and then I can either plot its imaginary component or phase. So, here is time, and this is phase of xn, and the phase could be, so it's, let us say this is 0, and it is in, let us say it is in radians, then the phase could be anything, I mean. So, this is for complex numbers. So, our discrete Fourier transform is able to handle complex numbers, and the relationship for converting this data into frequency domain is, so xn, where x is lowercase number, lowercase letter or small letter, and that is the time data, and the frequency data is capital X or uppercase xk, and that equals summation from n equals 0 to n equals capital N minus 1 xn e to the power of minus I 2 pi k n over n. Okay. Couple of things. Remember, so this relation is good if there are n points. So, this equation is good for data set n long. There will be n points, but the value of n, lower n, it does not start from 1, it starts from 0. So, it starts from 0 and it goes on to n minus 1. So, total number of points is capital N, but the value of lowercase n, this little n, it starts from 0. This is extremely important to remember. It starts from 0 and it goes on till n minus 1. So, we end up having same number of points, that is capital N. And here I equals the square root of minus 1. Okay? I equals the square root of minus 1. And value of k, it is also from 0 to n minus 1. So, if there are capital N points, I can calculate n values of x, x0, x1, x2, x3 dot 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 till x n minus 1, where n is uppercase, and I calculate the value of x0 in this equation. I add this whole equation over indice n, and here in the exponent term I put k is equal to 0. If I have to calculate x is equal x1, then it's the same relation. I still add up over the whole range n is equal to 0 to n minus 1, but the only thing which I do different is I put k is equal to 1, and so on and so forth, and I go on till I get n values of x, and the index of x starts from 0 and ends to capital N minus 1. Okay. Now I am going to express this relation in another form. So we have seen that xk is xn exponent minus I 2 pi kn over n. Okay. And this I can also write it as because e to the power of I times something, I can express it as a cosine as well as a sine, and this entire term which is in brackets is a real number, it is not complex, 2 pi k n divided by capital N. So the entire entity is real. So the exponent of e is imaginary. So I can have a cosine and a sine term. So this is equal to xn cosine 2 pi k n over n minus I sine 2 pi k n over n. Okay. Xn. So this is another form. So you can actually use this. So this is, these relations are known as DFT relations, and they help us compute the transform a time series data into frequency domain. Okay, into frequency domain. Now we will, I have still not said that xk corresponds to what frequency. I have not defined that, and I have also not said that xk is identical to the magnitude of the frequency at a particular frequency, magnitude of a particular frequency component, but xk is its representation. I will later change this xk into an actual magnitude component, but that we will see later, and also a phase component. So that we will see later. Okay. So let us do an example. Okay. So the example is that let us say my x is a function of time such that it is equal to 2 sine 2 pi ft. Okay. Where f equals, I want to make this problem simple, so I will say it is 1 hertz, and so using this formula, let us say I will generate points. I will generate points, so I will get x n. Using this formula, I will generate x n. For different values of time, I will put different values of time and I will get discrete points, and then I will see how I convert that discrete point into frequency domain. Okay. And then I can keep on generating these points forever, right. I can generate it for 1 second, 2 second, 3 second, 10 second, 20 second. So, I will generate xn for a time period of 3 seconds, let us say. So, I call this, so t, so this is not the period of the signal, this is the total duration of time, and that is 3 seconds. Okay. And the third thing is, so this is one parameter f, this is the duration of time, capital T, and then the third question which I have to address is how frequently I will find the points. So, I can calculate the value of this function every 0.01 second, I can calculate the value of this function every 0.1 second, I can calculate it every 0.2 second, right. So, what I will do is I will calculate it 8 times each second. Or this is called Fs. Thus, Fs is equal to sampling frequency and that equals 8 hertz. This is not the frequency of the signal, it is the number of times I am calculating this value each second. Okay. So, I have 3 parameters here. One is the frequency of the signal, second one is the duration over which I am calculating the value of xn, and then the third parameter is sampling frequency, which corresponds to number of times I compute the value of xn each second. So, that is what I am going to do, and what I have done is I have actually already done this, and this is how, okay, this is what I did. I actually used some equation, computed, and I have plotted the value of xt. Okay. So, this is the value of xt. So, xt was 2 sine times 2 pi ft. The frequency of this signal I specified at 1 hertz. Duration of signal was 3 seconds. So, I computed it. So, x axis is time. So, I have computed for 3 seconds, right. And then I calculated this value 8 times each second. Okay. So, this is 1 second. So, 1.2 times 3. So, how many steps we have? 1, 2, 3, 4, 5, 6, 7, 8. I have broken each second into 8 units. So, these are the discrete points. Each of these diamonds is a discrete point, and I have connected them with a straight line. So, my time domain data is not the line in between, because this is a discrete function. So, the time domain data is actually just the point, it is just the point. So, now I have generated these points, and then what I will do is that I will use that relation to calculate its Fourier transform, that is in frequency space. And if we do our mathematics correctly, then from these data, these points only, we should be able to infer that the amplitude of the signal is 2 and the period and the frequency of the signal is 1 hertz. So, that is what we should be able to do. So, we will do that in the next class, and thanks for listening, and we will see you tomorrow.